So a little bit about our speakers today. We're joined by two of my colleagues. We're being joined by Lee Kalcsits, who is an associate professor and also the endowed chair of tree fruit, environmental physiology and management at WSU, and also Dr. Lailiang Cheng, professor in the School of Integrated Plant Science in the horticultural section at Cornell University. And both of these two are part of a larger project that we are calling the Spark project through the USDA SCRI program. And a lot of this work is kind of based around this project that we're working on. And the project is preparing U.S. pome fruit production for extreme temperatures in a changing climate. So a lot of this work is going to be relevant to that. So with that, I'm going to turn things over to Lee, our first speaker.
All right, thanks, Mike. You can hear me okay? Sounds good.
Sounds good. Yep.
Okay, great. Sunburn on the East Coast it may not be the biggest issue you face, but as you saw this past summer, sunburn can pop up in your orchards and in apple orchards specifically. So it's something to consider, and so I'll kind of go through how it happens, what are the environmental factors at play, under some of the underlying physiology of sunburn, and then I'll cover some of the mitigation practices that are commonly used in Washington State, some of those that might apply and be useful for growers in the Northeast. Um, and then as orchards, as we move, and as generally the progression of orchards have moved from low density, really large trees with fairly large canopies to much simpler canopies and orchard systems that are more two-dimensional. There's less vegetative vigor, there's less leaf area. The risk for sunburn increases. So it's not just that, okay, in some years it might be exceptionally hot like this past year, but also changing orchard systems will change the risk. And I'll kind of go through some of those factors as well. So I'll cover, the definition of apple sunburn. What is it? What does it look like? And then how does it happen? So understanding how it happens on the individual fruit basis, and then how it happens on what determines how many fruit are affected in your orchard, based off of distribution of the canopy or your orchard systems or leaf area. And then I'll go through some of the mitigation strategies for sunburn. So what is apple sunburn? So just the simplest definition is any discoloration, any physical damage, or any death to the fruit surface caused by elevated fruit surface temperatures. So it's a combination usually of sunlight and high temperatures that cause, and much like, if we walk out into the sun in the summertime and you feel the sun on your skin and it feels hotter than the air feels. The apples feel the same. So they heat up more, and they have a higher surface temperature than the air around it, because it's a combination of radiant heating coming from the incoming solar radiation with the air temperature. And then it's damage that it can appear either in the field, shortly, maybe 2-3 days after sunburn inducing conditions happen, or it can also appear during storage. You might not see it at harvest, but it shows as delayed sun scald and can appear when you store fruit for 3 or 4 months. You start to see this sunburn or heat damage start to appear. So the most severe sunburn you can get, and we see this every now in Washington State on highly exposed fruit, where it's sunburn necrosis. So it's necrotic tissue that has been completely killed, and it's generally when the apple fruit surface temperature reaches 125 degrees Fahrenheit for just a short period of time. That's enough to kill the cells on the surface and cause necrotic damage. And it can also induce cracking. Obviously, that's going to be a cull. It can cause disease issues, and it can be a vector for pathogens to enter that fruit. And then also increase the risk for fruit around it, or if it gets picked to infect other fruit in that same bin. Sunburn browning, this is the most common type of sunburn we see in Washington State. On a normal year, if growers aren't protecting their fruit in any way, they can lose up to 20% of their fruit to sunburn browning. And it's a yellowing, browning, or bronzing, or development of a dark tan spot. So it's not necrotic tissue. It's not dead tissue, but it's heavily damaged. And it's a whole spectrum of damages. It could be really minor damage with slight yellowing of the peel, all the way to a dark tan, leathery type texture where the damage is so severe, but it's still not necrotic. So that skin layer, that peel layer, is not fully dead. This happens. So different varieties have different thresholds for sunburn to develop. Honeycrisp is one of the more susceptible varieties with a lower temperature threshold. So when fruit surface temperatures reach 115 degrees Fahrenheit, that's when sunburn brownie can start to appear in Honeycrisp. And for Crisp Pink, which we grow in Washington State, it's 120 degrees Fahrenheit, or maybe even slightly higher than that. So different cultivars have different thresholds. We don't really have a good idea, a good handle on all the cultivars. These are just some of the few that we know. We do know that there's variability in sunburn, browning, susceptibility among cultivars. That might be because of the physiology of the apple itself, or how the canopy grows around the fruit to protect the fruit from elevated fruit surface temperature. So it might be a combination of both. And we're working to figure that out in the Spark project. The last type of sunburn, and this is not temperature related. So this you could see in the Northeast, depending on how you're managing your trees, is photo-oxidative sunburn. So this is sunburn that happens when the peel chemistry of the apple is overwhelmed by sudden exposure to sunlight. So when it develops in the shade, it develops a certain chemistry of the peel, its ability to deal with light. And when it's suddenly exposed to really high sunlight, it can be damaged. So some of the factors or management practices that can affect the appearance of photo-oxidative sunburn in your orchard. Hand thinning. So if you thin the top fruit and leave the bottom fruit in a cluster, by suddenly exposing that bottom fruit to full sunlight, that fruit can get photo-oxidative sunburn. Heavy crop loads on branches, or thin branches. As the fruit grows and the branches move during the summer, you can have exposure of fruit to full sunlight after it develops in the shade. So you can get photo-oxidative sunburn from shifting of a branch as the fruit grows. And then also summer pruning. So summer pruning is often used to improve red color and improve light penetration into the canopy, and to control vegetative vigor, setting up fruiting buds for the following year. But it can also increase the risk of photo-oxidative sunburn on the fruit surface. So again, this is not a temperature-driven process. It can happen when the fruit surface temperature is actually quite cool. But under high light conditions, when that fruit's adapted to the shade, you can get photo-oxidative sunburn. So there's been a lot of models that have been developed to understand the factors that contribute to fruit surface temperature, because it's different than ambient, or the air temperature around it. So the air temperature could be 85 degrees Fahrenheit. And then the apple fruit surface temperature can be maybe 105, 107 degrees Fahrenheit. So it's roughly the apple fruit surface temperature is 20 to 22 degrees Fahrenheit more than the air. But it's not always like that. So you have air temperature that sets the baseline. You have solar radiation that sets the amount of heating that the apple can be exposed to. You have wind speed that affects how quickly that heat is pulled off the fruit surface. So the windier it is, the closer the fruit surface temperature will be to the air temperature. And then relative humidity affects the transfer of heat from the fruit surface to the air. So those are some of the environmental factors that affect fruit surface temperature. And then there's other factors like the apple diameter. So the larger the diameter, the greater the surface area of the fruit that is fully exposed to perpendicular incoming sunlight. And so larger apples have larger fruit surface area that could be heated up and generally at higher risk to sunburn than smaller apples. And then the apple albedo, which is the reflectivity of the apple, that changes during the season, during fruit development, and during harvest. The ability of the fruit to get rid of excess light and heat energy is lower, so it's more susceptible to sunburn as the fruit matures and that chlorophyll, that green background starts to degrade. The risk for sunburn is much higher. We can see this that different varieties are going to have different fruit development patterns. They're going to have different color means different ability to absorb light, and also that background color, depending on when that background color starts to degrade, its ability to dissipate heat and get rid of excess light energy. So that's why earlier cultivars generally are more susceptible to sunburn than later cultivars, because it's a hotter time of the year when that chlorophyll or green background starts to degrade when the fruit ripens near harvest. And then changes in tree architecture. So a lot of the models have focused on individual fruit and have not necessarily considered the full tree or the full canopy. And as we've gone from these low density, large apple trees on the left to medium density in the middle to this really high density, intensive, fully exposed fruit, because we want to get all we want to optimize red color. We want to have consistent uniform yield and quality and size. You want a nice planar canopy, but also that increases the fruit exposure to sunlight and increases sunburn risk. So a greater proportion of that fruit is exposed to full sunlight. And then in really hot days, you have a greater proportion of your fruit that is susceptible to sunburn. So there's going to be a trade-offs between red color and fruit sunburn, and this is just a simple diagram showing that really when you have on the left you have a simpler canopy with less vegetative material or vegetative canopy growth up high, and then on the right you have a little bit more thicker canopy, more complex. Well, the proportion of fruit that are all on the outer areas on the left is higher than the amount of fruit that is on exposed areas on the right. So that changes the amount of fruit sunburn, or the proportion of fruit that is at risk of sunburn in your canopy, but it also changes that red color balance. So it's important to balance that out. And then, there's a little bit of thoughts of, well, could you have a more vegetative canopy in the summertime when sunburn risk is higher, and then use de-leafers to remove that leaf material and expose more fruit to high sunlight and get better red color? Is there a balance or a management strategy in that? And that's something we're working on figuring out. That trade-off for the growers, and just to help them better inform their management strategies and understand that trade-off a little bit better. So current measures to mitigate sunburn. So there's three different main strategies. One being protective sprays they could either be reflective or UV blocking. The most common in Washington State, because we have a lot of irrigation water available to us, is water-based cooling or evaporative cooling. And then more commonly adopted in the last decade and a half is the use of overhead netting for high-value cultivars to protect the fruit without having to use water-based cooling. So protectant sprays, some of the examples are kaolin clay or sold as surround. There's also calcium carbonates on the market. Both of these just make the fruit whiter. Kaolin clay is really difficult to work with. The packing houses uh, aren't particularly fond of it because it's really difficult to clean off the fruit and get it ready for marketing. So it's not something that growers prefer to use. Calcium carbonate's a little bit better, but even then it's not as ideal as just not of it's not good for that overall fruit finish to put the reflective sprays on. But again, it's about balancing off the risk of sunburn versus not. There are chemical protectants, uh, UV blockers or insulating type materials that help protect the peel from sunburn. Rainox is one of them, so that's a UVB blocker, much like we put sunscreen on our skin to avoid UV rays. This Rainox is a carnauba wax-based product that blocks UVB. So there are products out there that either block UV or insulate the fruit, and and help protect the fruit from sunburn. But often these UVB blockers or UV blockers or insulating type materials, they're not a standalone type product that in Washington State we can't use them alone to protect from sunburn. I think in the Northeast there's maybe a little more potential for that because the fruit isn't that much over the fruit surface temperature threshold that a little bit of protection would go a long way. So something worth trying in the Northeast. Water-based cooling. So you could there's several different ways for water-based cooling. You could use it as hydrocooling, where you're just putting water on the tree. That cools the tree to some extent, but doesn't help prevent sunburn in really high temperature conditions. Um, Most commonly used is evaporative cooling. So it's using the cooling effect of evaporation of water, much like leaves cool themselves in the summertime by transpiring water from the leaf surface and keep that leaf surface cool. You could do the same thing by applying small amounts of water to your fruit, to an orchard, get the fruit wet, and then let all that water evaporate off. That has a strong cooling effect, pulls heat off the fruit, and then you let the fruit dry, and then you cycle again, and you run another cycle of water. You wet it and let it evaporate again. So that's the evaporative cooling. It needs that on-off cycling to get the optimum cooling effect. And then the last water-based cooling method is a fogging-based system where it's running fogging units, much like if you're out in the summer sitting on a patio, there's those misting sprinklers or misting units running to cool the air around that canopy. You don't really get wet, nothing really gets wet, but it cools the air. So it's a convective based cooling, meaning that it's cooling the air in the orchard, not necessarily cooling the fruit itself. Growers are using that more in Washington State, but the risk of that is, especially if you have hard water, is plugging of those fogging lines that can happen. And if you plug even just a small proportion of those fogging emitters, you can end up with high sunburn risk because you get zero protection at that point. So this is just an example of a sun-exposed apple on the left with fruit surface temperatures above 40 degrees Celsius. And then with evaporative cooling on, the fruit surface temperature does drop down. And then even with evaporative cooling off, so there's no water being applied, you're keeping that fruit surface temperature much cooler than a fully sun-exposed fruit. So I guess the major limitation of this is the high water requirement and the water quality requirement. Even with evaporative cooling systems, if you have salinity in your water or hard water, you can end up with water marking on the fruit, which can be a downgrade or a cull and difficult to deal with in the packing house. So water quality is highly important for evaporative cooling systems, even though they're highly effective. So I've kind of covered through some of this. There are some benefits for particle films for insect suppression, and as the fruit expands, so you might apply it early in the season because you have sunburn risk, and then the fruit grows and the fruit surface area increases, and you lose that effectiveness of the particle films or the Raynox. So you need to reapply these products frequently as the fruit's growing to provide adequate protection. And then shade nets, the idea of this is that it's reducing the incoming radiation, which then decreases the amount of heating that the fruit surface temperature has relative to the air temperature. Um, we did a whole bunch of work with color and density of nets. The density of nets can have a big influence. If you go too high, you can end up with poor return bloom, and too high of shading, you can end up with a poor return bloom and poor color development. But if you go too low, you're not providing the level of protection from sunburn that you need. The advantage of netting systems is that they also provide that hail protection, which is really important in the Northeast with the storms you can get and the hail risk that comes along with those storms. The downside of those is that they're expensive. The cheapest systems, netting systems now, either as a drape net or as a louver system, like you see on the right, those can be $3,000 to $5,000 an acre to install, plus the labor to deploy and deploy them in the spring and retract them in the fall. So they aren't cheap, and they're really meant for high value cultivars or high value orchard systems. We have seen some issues with red color for specifically for Honeycrisp that's hard to color. It depends on the nighttime lows. If you have conditions where that are difficult to color fruit, that netting is going to make it that much worse. But if you have really good coloring weather, the netting won't really have that much of an effect. So it really depends on the risk of poor red color development, and then the impact that netting will have on that red color. But it does provide a good protection from sunburn up until the air temperature reaches probably around 95 degrees. At 95 degrees Fahrenheit, if it's a clear sunny day, nettings start to lose their efficacy, and you start to need to, because then the air temperature is about 115, or sorry, the fruit surface temperature becomes about 115, and sunburn browning will start to happen even under net. So above 95, you start to need levels of protection for the fruit that go beyond the netting itself. But for 95% of the weather in Washington State, the nets do a really good job. This is just showcasing for Honeycrisp the efficacy of the different methods of sunburn protection for Honeycrisp. This was done in New York State. This was published in 2019, and this is just a graphical summary of the data from that paper. And you can see a sun-exposed apple at 44 degrees Celsius, evaporative cooling at 38 degrees Celsius, netting a little bit cooler than that, and then reflective sprays that are slightly above what evaporative cooling was. So you can see the ranking going from netting being the coolest, evaporative cooling being the second coolest, and then the reflective sprays being the least effective, but still effective at reducing the fruit surface temperature below the threshold for sunburn browning. So all of them work at providing a level of protection. This is work that was done in South Africa on Royal Gala. South Africa has much more sunburn pressure than New York State. So you can see the sun-exposed apple, incredibly hot, well above the threshold for sunburn browning. That's in the range of sunburn necrosis. You can see that the reflective spray cooled the fruit, but you're still probably going to see sunburn browning losses from using the reflective spray alone. But evaporative cooling and netting help protect the fruit a little bit more and kept the fruit below the threshold for sunburn browning or necrosis to happen. So with our current understanding of sunburn models, very often they only consider that individual fruit environment interaction, how that fully sun exposed fruit is interacting with its environment, and we determine risk by that fully sun exposed fruit. But what we don't really understand is how tree architecture and the distribution of fruit in the canopy affects the overall proportion of fruit that are affected by sunburn, and that can have a big impact. So how you manage that canopy, where that fruit's distributed, and then also cultivar levels of susceptibility, all that can determine uh, how much sunburn your orchards get that are independent of what that individual fruit environment interaction might show. So we're working on developing some more precise models that will allow for development of impacts of climate on sunburn risk and to better predict sunburn risk, both historically understanding that historical risk for growers and then also in the future. So this work was supported by our USDA Specialty Crop Research Initiative project, Spark. Just started. We're about a year and a half into that project. And with that, I'd be happy to answer any questions you might have. Thank you.
So with that, I'm going to turn things over to Dr. Cheng, who's going to talk to us about the effects of heat on fruit coloring.
Thank you, Mike. Good afternoon, everyone. I'm going to use the next 20-25 minutes to talk about how to enhance red color development in apple. We all know that the red color of apple fruit results from the synthesis of anthocyanins. As shown here, this process starts with an amino acid called phenylalanine, and then goes through several steps to produce anthocyanins at the bottom. This process starts with an amino acid called phenylalanine, and then goes through several steps to produce the red pigment we call anthocyanins. And this entire process is regulated by a protein called MIB1. Essentially, this protein regulates the expression of the genes encoding these enzymes involved in the process. And the amount of MIB1 protein is determined by the expression of its gene, the MIB1 gene. The gene has several versions, with each version called an allele. So as shown here, this MIB1-1 allele has a transposable element insertion in its promoter of the gene. The promoter controls the expression of the gene. So when you have an insertion here, it enhances the expression of this MIB1-1 gene, leading to more anthocyanin synthesis, making the fruit red. In contrast, let's say in Good and Delicious, and it has a different allele called MIB1-2. And this allele does not have the transposable element insertion in its promoter, leading to lower expression of the gene, and the skin basically stays, green or yellowish at harvest. So the bottom line is that the higher the expression of the gene, the higher anthocyanin synthesis. It has shown from different varieties, let's say red versus green varieties, and also in segregating populations. It's very clear that all the red varieties have this red transposon insertion in the promoter of the gene. All the green varieties don't have that. And also, you see here, the red skin progenies all have this red transposon element insertion. All the non-red progenies don't have this. So the higher the expression of the gene, the higher anthocyanin synthesis. Now, In red varieties, there's various degrees of red color. We all know that. This suggests that other genetic factors, such as other proteins, other genetic factors encoding proteins, that might alter the expression of MIB1, or other proteins that can interact with MIB1, changing its activity. We all know that Honeycrisp is more difficult to develop color, the red color, than Gala. And within Honeycrisp, both Firestorm and Royal Red strains develop color better than the original Honeycrisp, as shown here. Generally for the original Honeycrisp strain, the color won't develop until like starting around 2 weeks before harvest. And for the red strains here, they can get started at about 3 to 4 weeks before harvest. So using red strains is very important for getting better red color development in Honeycrisp. Among the manufacturers that affect red color development, crop load perhaps is the most important one, as shown here. This is a picture taken by Dr. Jim Shoup, 15, 20 years ago, but it illustrates the point I want to get across very well. So when you have a heavy crop load situation, the fruits just are not ready for red color development because their development and maturity gets delayed so much. So they are not ready, even if the environmental conditions are suitable for color development. In this situation, heavy crop load reduces the sugar level in the fruit. That would have an indirect effect on color development as well. At the other end of the extreme, at the other end, you see here, when you have very low crop load, fruits get very big and they have very high risk of bitter pit. They don't develop as good red color as the fruits in the moderate crop load treatment here. So achieving a proper crop load is critical for red color development, as well as for fruit size, bitter pit control, overall fruit storability, and return bloom for the next year. Among the environmental factors, light is a critical, it's essential for red color development. So shading in the lower part of the canopy decreases color development. With Honeycrisp, even for young trees, you'll have some level of shading in the lower part of the canopy. This is the result of two factors. First, Honeycrisp is a large fruited variety. As the fruit weight increases, it bends down the branches, making the branches hang downward here, creating shading. Second, each fruiting spur generally produces 2 borse shoots, creating shading to the fruit. So precision pruning during the winter and also during the summer, it's critical for crop load management. At the same time, it's also critical for red color development, because when you have better light exposure to the lower part of the canopy through pruning, you improve fruit light exposure, enhancing red color development. Now, this is an experiment we did 10, 12 years ago, where we turned fruits 180 degrees at about 10 days before harvest. We used 2 varieties. One is a red skin variety called Fortune. The other is a yellow skin variety called Mutsu. within a day and a half, you're going to see this rapid increase in MIB1 expression. So the gene that encodes the protein MIB1 is increased by about 35 times in fortune versus about 10 times in Mutsu. This leads to a rapid increase in anthocyanin synthesis. You see that this is 6 hours, this is about 30 hours. You see, we saw some anthocyanin synthesis already. Within like 5 to 7 days, you're going to see a fully red surface. And even for Mutsu, a yellow variety, within 5 to 7 days, you're going to see a red blush. Of course, the anthocyanin synthesis or the anthocyanin level is still significantly lower in Mutsu than in fortune, as shown here. But you're going to see some anthocyanin synthesis. This illustrates the importance of light for anthocyanin synthesis, and also provides a mechanism for us to enhance red color development near fruit harvest. Another important environmental factor for color development is temperature. This slide shows you the relationship between the daily average temperature and the anthocyanin synthesis rate. This work was done by Dr. Lee Creasy in the late 1960s on Macintosh. As you can see here, when the daily average temperature reaches about 70 degrees, and this the graph on the left was the data from 3 years work on the trees growing in the field, and the figure on the right shows you the data obtained on growth chamber grown trees. Generally, when the daily average temperature reaches 70 degrees Fahrenheit, you see very little anthocyanin synthesis. Okay, with decreasing daily average temperature, let's say from 65 to 50, you see almost a linear increase in anthocyanin synthesis. With climate change, we have apples, mid-season varieties ripen at earlier dates. For example, in 2024, we harvested Honeycrisps in early. We harvested Honeycrisp apples in early September instead of the mid-September, the normal harvest date. So with the harvesting date moving up, the fruit's going to have a higher chance of getting or experiencing higher temperatures. But there's not much we can do with fruit temperature except evaporative cooling. Lee just talked about that. In the East, we have not used that much in the past. Another environmental factor that affects fruit color development is nitrogen supply. As you can see here, low nitrogen supply promotes color development, but it reduces fruit size and increases biennial bearing risk. High nitrogen supply improves fruit size, but decreases color development, and also increases the risk of bitter pit and decreases fruit storability. So the tree nitrogen status that balances these opposite effects is the nitrogen level we should target for. So for this, for Honeycrisp, we found that its leaf nitrogen level right around 2%. 2% to 2.1% is the target we should use, the optimal nitrogen level we should use. We measure leaf nitrogen level at the end of June and also in early August, very similar responses. So target leaf nitrogen at the end of June, right around 2%. don't exceed 2.2%. So here is a list of strategies we can use to enhance red color development in Honeycrisp. First, we want to use strains that can still develop good color at high temperatures. Second, we need to adjust crop load to medium level using precision crop load management strategies. Terrence's group or the project, SCRI project, Pac-Man project has developed. So 4 to 5 fruits per centimeter square trunk cross-sectional area for year 3 and 4, 5 to 6 fruits per centimeter square trunk cross-sectional area from year 5 to 8. Third, want to ensure optimal tree nutrient status. For nitrogen, we shoot for 2%, right around 2%. For potassium, we shoot for 1 to 1.3%. For Honeycrisp. For Gala, that number for leaf potassium is 1.3 to 1.8%. As I mentioned earlier, because there's not a whole lot we can do with the climate, so we need to use sort of other ways to improve fruit color to compensate for the negative impact of high temperature on red color development. There are 2 approaches here. One is to increase fruit light exposure using partial canopy defoliation and reflective ground cover near harvest. And then the second approach is to use growth regulators. Let's look at the first approach. We did partial defoliation trials on Sweet Tango first, as you can see here, with increasing degree of canopy defoliation in the lower half of the canopy, we saw an increase in red color on the fruit. So this is the percent of the fruit surface covered with red color. So from about 20% to 40%. However, that was accompanied by a linear decrease in bud nitrogen level during the dormant season. During the winter, we measured the bud leaf nitrogen level. We saw a linear decrease. The good news is that this decrease can be fully compensated for by 2 applications of foliar urea at 3%, which is about 25 pounds of urea per 100 gallons of water. I'll explain why maintaining bud leaf nitrogen level is important a little later. We also did a partial defoliation trial with Gala. In this case, we used a pneumatic defoliation at about 50% to the lower 50% of the canopy, to the lower half of the canopy. As you can see here, Gala is a lot easier to develop color than Sweet Tango. See here, this is 55%, but there is a significant increase to 70%. Again, 2 foliar urea applications after harvesting the crop fully compensated for the negative impact of partial defoliation on bud nitrogen level. We did a very similar experiment with raw red Honeycrisp, as seen here, as shown here. So 50% defoliation to the lower part of the canopy. We saw a significant increase in red color. However, we found that one tree where we accidentally left 50% more crop, and then this tree did not respond to partial defoliation at all. Actually, if you look at the percent red color on those fruits, and this is even lower than the undefoliated control. This indicates the importance of getting the crop load right to red color development. So achieving a proper crop load is critical for red color development, as well as for fruit size control, bitter pit control, and return bloom. Now let's go back to the body nitrogen issue. It's consecutive defoliation, let's say defoliation at 50% level to the lower half of the canopy over consecutive years is expected to weaken the lower half of the tree. Because we found that in Macintosh, this work was done about 20 years ago with the Terrence. We found that Macintosh yield per tree is closely related to the spur nitrogen level. When the spur nitrogen level gets below like 1.25, you're gonna see significant drop in yield. And the yield per tree is not closely related to reserve carbohydrate level. So when you use 50% defoliation to the lower half of the canopy, for 2, 3, 4 years, you're gonna see a gradual decrease in spur quality, which is reflected in total spur leaf area, fruit set, fruit size. So using foliar urea application after fruit harvest is important for sustaining spur quality and productivity. Now, we can also use reflective ground cover. There are typically, 2 types. One is like one-time use, this mylar type. The other is the extended reflective ground cloth. And generally speaking, extended ground cloth performs much better than the mylar type. As shown here, you see this is Honeycrisp in 2021 experiment, a trial done by Dr. Terrence Robinson's group in Geneva. You can see here both mylar and extended improved red color. But the improvement by extended is significantly better than mylar. In Snapdragon in 2022, as you can see here, mylar is here, and the extended is here. This is, I think, started in 2021 or 2022. The company had produced a version of extended with better reflection. So the original one was, reflection is about 80%. The new one is about 90%. Now, growth regulators can be used to improve fruit color. So this shows you some of the data obtained by Dr. Terrence Robinson in Geneva, about 10 years ago. See here, this is the control. This is blush, 2 applications, one at 3 weeks before harvest. The other is at 1 week before fruit harvest. So it's a combination. It's 2 applications at 3 weeks and 1 week before harvest. You see this blush application significantly increased red color of Gala and also significantly increased red color of Fuji. However, there's a large variation between years. Some years you see this significant improvement, but in other years you don't. When you see this improvement in red color, we did a simple lab experiment where we just spray Gala with 3 levels of blush, 240 ppm, 480 ppm, and 720 ppm. I think that in the product only allows the use of a maximum of 480 ppm. but for the lab experiment, we purposely increased its level. We found that some of the genes involved in anthocyanin synthesis, such as the MIB1 gene and also the gene that encodes the enzyme that catalyzes the very last step of anthocyanin synthesis, both are increased. We also found that blush treatment increased the expression of the ethylene response factor, the ERF3, as you can see here. So indicating that blush regulates red color development partially through ethylene, the ethylene pathway. We also found a couple other proteins that can increase red color development in response to the blush treatment. So it's a combination of the ethylene pathway and also some pathways regulated by other proteins. Now, because blush can increase red color, we all know that retain application before harvest significantly reduces red color. So the idea is that can blush counter retains drag on red color development. This work was done early, like about 10 years ago on Honeycrisp. In that trial, we did see the effect of blush on countering retains drag on color development. And with the development of Exceed, Terence tried a combination of retain with Exceed on Gala. See the untreated control with retain application, let's say 21 days before harvest. And another treatment is a split application, 21 days and 7 days before harvest. You see a drop in red color development. And Exceed application alone, you see numerically improvement in red color, but may not be statistically significant. And then Exceed application with retain, see that? And this is retain at 21 days before harvest, followed by a retain and Exceed application at 7 days before harvest. Generally in Gala, we can see this sort of, Exceed application can counter the drag on red color development by retain, but in Honeycrisp, we have not seen a sort of significant effect. Although some of the work by another lab down in Virginia with repeated application of Exceed, you can see some, improvement in red color when it's used with retain, or use retain first and followed by Exceed application. It's very obvious that there's a lot we still need to do to figure out the best combinations, the dosage response and the timing and the combinations. So a quick summary on these last two approaches. Both partial defoliation and reflective ground cover are effective in improving red color by increasing fruit light exposure. Application of growth regulators, blush and Exceed in combination with retain near harvest can improve red color development, but their effects vary from year to year. Some years we just don't see any significant effect. Other years we see a significant effect. I think crop load is a very important factor here. Generally, when we don't see a significant effect, the crop load is on the heavy side. I think other factors may come into play, like environmental factors. Let's say if you get a lot of rainfall, a lot of cloudy days with plenty of rainfall, and that typically elevates fruit nitrogen status at harvest. So a lot of environmental factors can play into this, and definitely more work needs to be done in this regard. So at the very end, I want to thank all the people who did the work, all the cooperating growers, farms, fruit farms listed here, and the USDA NIFA project preparing U.S. palm fruit production for extreme temperatures in a changing climate, and New York Apple Research Development Program for supporting some of the earlier work. With that, I'm gonna stop. Yeah.
Well, thank you very much, Lailiang. We're just about out of time. Thank you so much for presenting with us today. I'm not sure if Lee's still here, but a big thanks to him as well. Thank you all for listening. Have a great afternoon.